This video is the first of 3 videos that I have created to talk about the phase relationships for soils. In this video, I first introduce the phase diagram, and then I will explain the basic parameters in the soil mechanics that help us understand the soils and their behaviors. Let's first see what is a phase diagram. Let's imagine this is a bucket full of soil, or it is a soil sample from a certain depth under the ground. This soil sample has the total volume of V sub t and the total mass of m sub t. This soil sample includes solid particles, which are these orange particles in this sample, and also some voids that are filling the gaps between these particles. These voids typically consist of water and also air. And typically, the more voids a soil has, the more problematic that soil could be. So in order to understand voids and their effect in soils, we use phase diagrams. A phase diagram is basically a way to divide and present the 3 components of soils. The phase diagram is an imaginary way of showing the soil sample that is in this bucket, with this difference that it is like the solid particles here are melted down in the sample, and then the water sat on it, and then the air sat on top of the water. The importance of using a phase diagram is that we can show how the total volume and the total mass are divided between the 3 components of the soil that are air, water, and solids. So if you look at this left side, the mass side, we can see the total mass is equal to the mass of solids plus the mass of water. And obviously the mass of air is equal to 0. And then if you look at the right side, the volume side, you can see the total volume of a soil sample is equal to the volume of solids plus the volume of voids. And then we can also see here that the volume of voids in a soil sample is equal to the volume of water plus the volume of air. Now you may ask, which one of these volumes and masses we can measure in the lab? The answer is that in a soil lab we can measure the total volume, the mass of solids, and also the mass of water. And then once we have these 3 values, we can calculate all the other masses and volumes within a soil sample. Now we hopefully better understand the phase diagram and are ready to learn about the basic parameters in soil mechanics that are based on phase relationships. These parameters can be divided in 3 categories. The first one is the one that is only based on volumetric ratios. The second one is the one that is only based on mass ratios. And the third one is the one that is based on the ratio between masses and volumes. The first parameter that we want to talk about is based on the volumetric ratios, and it is the void ratio. Void ratio is shown by E and is equal to the ratio between the total volume and the volume of solids that are shown here. The void ratio is typically expressed as a decimal, and mathematically the values of void ratio can be anywhere between 0 to infinity. Let's imagine you have a solid rock sample in which the volume of voids are equal to 0. In this case, the porosity of that rock sample is also equal to 0. On the other hand, imagine you have a soil sample that has a very large volume of voids. In that case, the void ratio of that soil sample will be infinity. But practically, the typical values of void ratio in sands is somewhere between 0 to 1. And in clays, it is somewhere between 0.3 to 1.5. The next parameter here is the porosity. The porosity is shown by N and is equal to the ratio between the volume of voids and the total volume, which you can see here. The porosity numerically shows how much voids we have in our soil sample within the total volume. Porosity is typically shown as a percentage, and mathematically the values of porosity can be anywhere between 0 to 100%. The zero porosity will be when we have our rock sample in which the volume of void is equal to 0, and the 100% porosity is something that doesn't happen in practice, but is where the volume of void equals to the total volume. Basically, where the volume of soil particles is equal to 0. In this case, the porosity will be 100%. Now that we are familiar with void ratio and the porosity, let's see how we can derive an equation that relates these two. So let's start with the equation for the porosity, which is N is equal to V sub void divided by the total volume. Now, in this equation, we can replace V sub T by the V sub S plus the V sub void. Then, if we rewrite this equation, we will have N is equal to V sub V divided by V sub S plus V sub V. Now, the next thing that we can do here is that we can divide both numerator and the denominator by V sub S to be able to find the void ratio equation here. So as you can see, in the numerator, we derive the equation for E, as well as in the denominator, and then V sub S divided by V sub S is equal to 1. So we can finally write the equation that relates these two, which is N is equal to E divided by 1 plus E. So we could also start from the equation of the void ratio, which was E is equal to V sub void divided by the V sub S. And if we had taken similar steps, but with just a little bit of difference, we could find the other equation that relates N and E, which is E is equal to N divided by 1 minus N. These two are very important equations that we can use a lot in phase relationships problems. Now, there's another equation that is really helpful to use in phase relationships problems. That is the equation that relates E, V sub T, and V sub S. So to derive this equation, let's just start with the equation of the void ratio. Then what we can do is that we can add 1 to the both sides of the equation. So we can write E plus 1 is equal to V sub void divided by V sub S plus 1. Now, the one on the right side of the equation can be replaced with V sub S divided by V sub S, which is equal to 1. So we can rewrite this equation as E plus 1 is equal to V sub V divided by V sub S plus V sub S divided by V sub S. So we can get a common denominator between these two fractions and write E plus 1 is equal to V sub S plus V sub V, or V sub V plus V sub S divided by V sub S. So we can see that in the numerator we have the total volume. So finally we were able to derive the equation that we wanted, that relates E, the total volume, and the volume of solids, which is E plus 1 is equal to the total volume divided by the volume of solids. The last parameter to talk about in this category is the degree of saturation, which is shown by S sub R, or sometimes S, and is equal to the ratio between the volume of water to the volume of voids. This parameter simply quantifies how much water exists between the volume of voids in our sample. This parameter is usually expressed as a percentage, and both mathematical and practical values of the degree of saturation are anywhere from 0 to 100%. When the degree of saturation is 0, the sample is called a dry sample. When it is 100%, the sample is called a saturated sample. In a dry sample, as you can see from the equation, the volume of water is equal to 0. In a saturated sample, the volume of water is equal to the volume of voids. So all the voids in this sample are filled with water. Therefore, the volume of air is equal to 0. And all the other samples that have saturated degrees or degree of saturations between 100% to 0 are called partially saturated samples. Alright, now we are done with the first category and we can move on to the next one, that is only based on mass ratios. In this category, we only have one parameter, that is the moisture content. Moisture content is defined as the ratio between the mass of water to the mass of solids in a soil sample. This parameter is normally expressed as a percentage, and the typical values of a moisture content can be from 0, which is in a dry sample, which has a mass of water of 0, to a very, very large number, which will happen in a sample that has, as far as mass, has a mass of water that is much larger than mass of solids in it. The last category that we want to talk about here today is the category that is only based on volumes and masses of a soil sample, and the only parameter here is the density. We are all familiar with densities from physics and chemistry, and we all know that density is mass per unit volume, and it is shown by rho, and the equation based on the definition is mass divided by volume. So in the geotech engineering, when we talk about the densities, we can talk about 3 different densities for a soil sample. The first one is the density of the soil as a whole. The second one is the density of the solid particles. And the third one is the density of water. We all know that the density of water is known, and it is equal to 1,000 kilogram per cubic meter, or 1 gram per cubic centimeter. The density of the sol is shown by rho usually, or it's sometimes shown by rho T, and T stands for the total, and is equal to the total mass divided by the total volume. On the other hand, the density of the solid particles is usually shown by rho sub s, and s stands for the solid particles, and it is equal to the mass of solids divided by the volume of solids. As far as the values of rho sub t and rho sub s, we can say that rho sub t, or the total density of sol, can be anywhere between 1000 to 2400 kilogram per cubic meter. And the density of the solid particles, on the other hand, can be anywhere between 2500 to 2800 kilogram per cubic meter. The last thing to mention here is that the unit of the density is kilogram per cubic meter in the SI unit, as we were saying here, and then in the English unit, the unit is pound per cubic feet, which is also shown as PCF. In talking about densities of sols, there are a few densities that are very important to know and use in phase relationship problems. The first one is the saturated density. Saturated density is the density of the sol sample when all the voids in the sample are filled with water, or in another word, the volume of air is equal to 0. In this case, the equation is shown by rho sub sat, and it will be mass of solids plus mass of water divided by the total volume. The other important density that a sol has is the dry density. Dry density is pretty much used a lot in compaction problems. The dry density of a sol is when there is no water in the sol. So mass of water is equal to 0. So looking at the equation above, we can say that dry density is equal to only mass of solids, because it will be the only mass in a sol, divided by the total volume. And then the last one is the submerged density. I'm going to make a separate video to explain the buoyancy effect and the submerged density, but for now let's just say the submerged density is shown by rho prime and is equal to the saturated density minus the density of water. There are two more parameters that I did not include in the list of parameters on top that are kind of related to the density, and we are all again familiar with them from physics and chemistry. The first one is the specific gravity. Specific gravity, by definition, is equal to the ratio of the density of an object to the density of water. And in geotechnical engineering, when we talk about a specific gravity, we are interested to know what is the specific gravity of the solid particles. So we use rho sub s here, and then we call it g sub s, and s stands for the solid particles. The second parameter and the last parameter in this video is the unit weight. We all know what the unit weights are. Unit weights are density times gravitational acceleration. And as density was mass divided by volume, when we multiplied mass by gravitational acceleration, we only have weight divided by volume. So whatever densities that we had in the previous part of this video, if we multiply it by g, we will have a unit weight for that. For example, we had the density of solid particles. If we multiply it by g, we will have the unit weight of solid particles. We had the density of dry sample. If we multiply it by g, we will have the unit weight of dry sample. We had the density of water. If we multiply it by g, we will have a unit weight of water, and so on. So this concludes this video that was about the phase diagram and some of the most fundamental parameters in solid mechanics. I hope you liked it. Please let me know in the questions if you have any question, and I hope you will see the other videos that complement this video.